Okay, welcome back, welcome back. So anyway, these people in chat were figuring out I'll be less helpful for you know questions about the exam, unless it's something like I don't understand like the words in the question sort of questions, but I feel like there's probably not going to be that much of those. So anyway, so we are in the home stretch. Typically, like in a typical course in 240 or 461, so I've been involved in writing, the uniform finals for these courses like many, many times, and typically the last section on these, like from the textbook that is something that all classes will have been expected to see is 7.2. Sometimes if it's been a semester where there's been absolutely like no snow cancellations or anything like that, sometimes there will be some kind of constraint optimization problems showing up uh, on the final exam, like one question or something. But typically 7.2 is like the end of the road for the course, and after that it's just kind of whatever the instructor wants to cover. And so I'll do that. We'll have at least one fun day where I talk about something random that's not in the textbook. But anyway, so we're starting chapter 7 today, and it's going to require me finishing what I want to mention in this first section of chapter 7 is going to require me going way back to 2.4 in the textbook, which it was a section I actually skipped back then, and I only need one thing from it, but I skipped it because it kind of had no purpose at the time. Will the final also be take home? Yeah, final will also be take home. Okay, so the big topic, which I've already put in the YouTube description, is the notion of a symmetric matrix. So quick definition, and I might have already defined this when we came across them before, but a matrix A is symmetric if A transpose is equal to A. Okay. So if you have a matrix that's equal to its own transpose, it is called symmetric. Now, intuitively, just thinking about it for 2 seconds, like what does that tell you? If it's equal to its own transpose, one, it's got to be square, right? Since transpose switches the roles of columns and rows. So, you could not have an m by n matrix be equal to an n by m matrix. So it's necessarily got to be square. So note that if you have that a matrix is symmetric, it's got to be square. So even if it doesn't say it's square, right? So A symmetric implies that A is square. All right, so that's one thing. Another thing is if you were to just look at a matrix, right, you would be able to tell whether or not it's symmetric based on this criterion because it would be symmetric across the diagonal, right, is what this is saying. Okay, so it would have symmetry across the diagonal. Here's some examples. All right, so here's examples of symmetric matrices. So here's one. Let's just say 5, 0, 0, minus 3. All right. Now, this is a 2 by 2. That might not look symmetric, but it is, right? What's the transpose of this, right? If I take the transpose of this, the row 5, 0 goes to the column 5, 0. Okay, and the row 0 minus 3 goes to the column 0 minus 3. Oh, yeah, that's symmetric, right? Well, let's look at another example. So let's pick 3 by 3 here. So I'm going to fill out the diagonal here. And I could ask you the question of, does it matter what I've put on the diagonal there? Like, is this, well, okay. It really depends on, what sense I'm talking about, right? I mean, does it matter in the sense of, have I constrained myself at all with what's happening going forward? Right? Like, did any of my choices here impact what can go in these other entries? Right? The answer is no, right? It's not, didn't impact anything. So if I put, say, a 2 here, did that choice impact what can go in the other entries? Yeah, right? If I have a 2 here, well, then a 2 must be also right there. Okay, similarly, if this is a -7, then I have to have a -7 over here, right? I'm thinking of this diagonal being like a mirror, right? And so, similarly, if this is a 3, then this has to be a 3. Okay. And so that's how this goes. Now, of course, it didn't matter what numbers I put in here. So one way to also show exactly what's going on here, I could do exactly, what I did there, except with just generic letters instead. So I'm going to call my diagonal, say, A, D, and F here. Okay, it's kind of hinting on how many is needed. So the second I put a B here, B has to go here. And the second that I put a C here, well, C has to go on the opposite side, and similarly for E, right? Okay. And so this is how a symmetric matrix is. You see that in filling one out, the second you put an entry here off the diagonal, well, then that's constraining you somewhere else in the matrix. Okay. All right. Of course, the examples of non-symmetric matrices are easy, right? It only has to fail at a single entry, right? You can have I know it might be stupid to have a category for non-symmetric matrices since most matrices are non-symmetric, but here, I'm just going to list one that's funny, that's not symmetric, to trick you. So here we go. There we go. Right. So that's not a symmetric matrix, right? Even though this matrix is symmetric with respect to like the off diagonal, right? It's not a symmetric matrix because when we talk about symmetry, we only care about symmetry across the main diagonal, and so there's bad reflections there, right? They don't match up. Okay, so anyway, so that's the deal. Now, I could go ahead and try to, give you a symmetric matrix and you diagonalize it to see what happens. Rather than do that, I'm just going to tell you what it is that goes on, since we spent a good amount of time on diagonalization. So I think that you've had plenty of chances to practice it, so I don't need to work through a full diagonalization problem again right now. And so, big question is, what's nice about symmetric matrices? Right? I mean, like, aesthetically, they're kind of nice, right? If you imagine going to, like, the doctor's office, and I don't know, actually, maybe this shows my age. I don't know what they put in doctor's offices now, but when I was a kid, there were these magazines called, they're called, like, Highlights, and there were these magazines for kids. They had things like, it was like an image, you had to find a bunch of stuff, so they'd have like a list of, find like a rabbit, find like a hat, and it was hidden in the image somewhere. And then they also had these exercises where they had like half of a face drawn, and you had to draw the other half like symmetrically. So, like aesthetically, a kid could fill out a symmetric matrix if you gave him half and you explained that, the diagonal is a mirror, right? So an elementary school student could actually complete a symmetric matrix or complete half a symmetric matrix to make it symmetric. So what's nice about symmetric matrices other than the aesthetic properties? Well, you'll see. You'll see what's nice about them in terms of diagonalization and in terms of eigenvalues and eigenvectors. You'll see what's so nice about them. It turns out they are extremely nice. Okay, they are like some of the nicest. There's like one of the nicest classes of matrices you can have. So here's partial answer. By the end of this section, we'll have a full answer for why they're so awesome. If A is symmetric, Then any two eigenvectors from different eigenspaces are orthogonal. So that's pretty awesome. Okay, just on its face, that's a nice property to have. And this actually leads us to terminology that we'll introduce specifically for symmetric matrices, and you'll see why. So here's the definition. Okay. Let's say we have a matrix A, and we want to talk about diagonalizing a matrix A, but we want to talk about diagonalizing it where the change of coordinates matrix P is an orthogonal matrix. Right? So A n by n is said to be orthogonal, or orthogonally diagonalizable. Okay, if there exists an orthogonal P, so an orthogonal matrix. Remember, if it's an orthogonal matrix, its columns are orthonormal. So an orthogonal matrix P, and of course, since it's orthogonal, P inverse is the same thing as P transpose. All right. Maybe if you look at that and you're like, wait, what do you mean P inverse is P transpose? Remember this statement for orthogonal matrices? Actually, this was a statement not just for orthogonal matrices. This was a statement more generally, even for rectangular matrices whose columns were orthonormal, that was true. Right? Okay. So there exists an orthogonal matrix P, and of course, if it's an orthogonal matrix, then its inverse is just its transpose. Okay. And a diagonal matrix D such that A is equal to P D P inverse, or P D P transpose. So what is this? I mean, the easiest way to say it in words is just, if a matrix is orthogonally diagonalizable, it means it's diagonalizable, but the matrix P that diagonalizes it is an orthogonal matrix, right? But remember how we did diagonalization. How did we construct P, right? If a matrix is diagonalizable, P was constructed from the eigenvectors we found, okay? And since a matrix being orthogonal means that its columns are orthonormal, right, or form an orthonormal basis, right, for Rn, then it means that you have a collection of orthonormal eigenvectors. Well, having a collection of orthogonal eigenvectors would do it, right? Because we can always just scale them individually, and that doesn't change anything. And so this theorem that I wrote here is very crucial for discussing orthogonal diagonalizability, because constructing matrix P requires having a bunch of pairwise orthogonal eigenvectors, right? In fact, not just a bunch, but as many as you need, right? You need n of them, okay? And so it turns out that if I ask the question, what kinds of matrices are orthogonally diagonalizable? Right? Because this is like above and beyond being just diagonalizable. This is like, you're diagonalizable, but also the diagonalization matrix is, you know, orthogonal. So it's like really, really nice. Okay, it's basically as nice as possible. If I ask the question, what kinds of matrices are orthogonally diagonalizable, the answer is symmetric matrices, and that's it. And no others. So yeah, it turns out that symmetric matrices are the only examples of matrices that are orthogonally diagonalizable. So this is another fact that shows you how nice symmetric matrices are. So this question and answer bit is actually the contents of the theorem that I'll restate for the purposes of it looking nice. So there's this theorem, a matrix that's an n by n matrix is orthogonally diagonalizable if and only if A is symmetric. So only symmetric matrices are orthogonally diagonalizable. Okay, and every symmetric matrix is orthogonally diagonalizable. So this is pretty amazing. Why is this maybe even more amazing than it might seem? So maybe I'll state this. So why is this so nice? The answer is this suggests that there are matrices. I mean, this doesn't just suggest, this tells you exactly that there are matrices that you can tell are diagonalizable. In fact, orthogonally diagonalizable. So diagonalizable in the best way. So diagonalizable. You can tell that they are diagonalizable just from a glance, right? Just from looking at them. Because if you look at a matrix, you can tell whether or not it's symmetric, right? Now, yeah, if you have like a 500 by 500 matrix, then then that might be kind of annoying to check with your eyes. But if you think about it in terms of like computing, feeding in a 500 by 500 matrix into a program and having it check that it's symmetric, how would you do that? All you're doing is just comparing a sub ij entries to a sub ji entries, right? So you're literally just swapping the indices there. So you just compare like that, and a computer could do that in like a nanosecond or something. So comparing, like finding out that a matrix is symmetric takes no work at all, and it immediately tells you it's diagonalizable, right? But from what we did with eigenvalues and eigenvectors and doing all this diagonalization stuff, out fully, you might have been led to believe that it was impossible to just typically glance at a matrix and see whether or not it's diagonalizable. But this tells you that actually for the case of symmetric matrices, it's really easy. Okay. And so this is really nice. And there are examples you can do that actually show how nice this is. But of course, I'm not going to go through those since we actually just worked out some of those very recently in chapter 6. I just did an example of a nice constructing orthogonal matrix that actually did this very thing. Okay, so now the big named theorem that kind of ties together how nice all of this stuff is. So we have one more. Very nice fact about symmetric matrices. And this is called the spectral theorem. It's called the spectral theorem because the spectrum of a matrix is an old way of talking about its eigenvalues. So whenever you hear the word spectral something, it's usually referring to eigenvalues. I guess spectral sequences don't don't fit that example, but that's okay. Anyway, okay, so theorem, the spectral theorem. What is the spectral theorem? So this is the spectral theorem for symmetric matrices, but we'll just call it the spectral theorem. So let A be an n by n matrix. So let A be symmetric. Then here's a list of properties that A satisfies. Then A has the following properties. Okay, so first property, it has n real eigenvalues counting multiplicities. Okay. All right. That's really nice. I mean, it tells you it has no complex eigenvalues, right? So it's only got real eigenvalues. So that's a really nice fact. Second, the dimension. So the dimension of the eigenspace for each eigenvalue, lambda, equals the multiplicity of lambda as a root of the characteristic polynomial. Okay. All right. Next, the eigenspaces are mutually orthogonal in the sense that eigenvectors corresponding to different eigenvalues are orthogonal. So the eigenspaces are mutually orthogonal. So we got that from that first theorem we wrote today, which said that eigenvectors from different eigenspaces were orthogonal. So the eigenspaces are mutually orthogonal, right, i.e. eigenvectors corresponding to different eigenvalues are orthogonal. Okay, and one more thing, which we've already seen, A is orthogonally diagonalizable. Okay. And so here is just a list of really nice properties that a symmetric matrix has. Okay. Now, what is maybe like a resulting thing that comes out of this that makes this so nice? It's something called the spectral decomposition. So in order for me to have the spectral decomposition make sense, I have to go back to something that I'd skipped earlier in the semester. So that's what I'm about to do now. So in addition to these nice facts, we have what's called, so we also have a spectral decomposition for A. Or of A. Okay, but to understand this, I have to go back and understand, so I need material from 2.4 for this. Or else it doesn't really make sense. Okay. So 2.4 was a section that we had skipped over. And the reason we'd skipped over it had to do with, it was mostly dealing with partitions of matrices and block matrices. We'll return to this when I talk about the Jordan canonical form, which is what I'm going to do. It's like the one thing that's not listed in the textbook, and it's like the one thing in the course description for Math 461 that is listed in 461 but not listed in 240, I think. At least it was like that a couple years ago. So I feel like, to be legit and have this be a Math 461 course and not just a clone of Math 240, I have to mention the Jordan canonical form. So I will do that, and we'll be back to dealing with partitions and block matrices then. But I don't need that stuff right now. All I need is called the column-row expansion. Okay, so what I need is, so this is way back. This is from 2.4. And this is called column-row multiplication. And this is going to lead to something called the column-row expansion for a matrix product. Okay. Now, what is an example of this? Kind of, rather than go through and define this like totally generally, I'm going to do a single example that illustrates what I mean by this. So what is column-row multiplication? Okay. So I'm going to start with two matrices. I'm going to call those matrices A and B. And A is going to be the 2 by 3 matrix, -3, 1, 2, 1, -4, 5. Okay. And B is going to be the matrix that is made up of completely general letters here. So A, B, C, D, E, F. Okay. And B is a 3 by 2. Okay. So I want to check that the product A times B can be thought of as column sub 1 of A times row sub 1 of B plus column sub 2 of A times row sub 2 of B plus column sub 3 of A plus or times row sub 3 of B. But what do I mean by this? What do I mean by this? Well, that's what I'm gonna show you now. Okay, so what do I mean by column 1 of A times row 1 of B? What does that mean? So what this means is column 1 of A times row 1 of B. I write that as the first column of A is -3, 1, and the first row of B is AB. Okay, so I write them like that. Now, what do I mean when I say column 1 of A times row 1 of B? How am I multiplying these? It's not the normal multiplication, right? I mean, it couldn't be. This is a 1 by 2. This is a 2 by 1. This is a 1 by 2. But what would that give me? This would give me some. So this should give me a 2 by 2, right? And what 2 by 2 should it give me? So the way that this works is that this is -3A -3B AB, because it's just 1 times A, 1 times B. Huh. Okay, that's weird, right? That's not the normal way that things work. Okay, but let's continue. What would column 2 of A times row 2 of B look like? So this would be the column 1 -4 and times the row CD. And so this would be CD, and this would be minus 4C minus 4D. Okay. And then lastly, column 3 of A times row 3 of B is 2,5 times EF. So this is 2E 2F and 5E 5F. Okay. Now, what is the point? The point is that if you actually compute this, so what is this? I'm going to write this using sum notation. So this is the sum from I equals 1 to 3 of col sub I of A rho sub I of B. If you actually add these three terms together, what do you get? So you get the 2 by 2 matrix that is, so this would be minus 3 plus C plus 2E, or sorry, minus 3A plus C plus 2E. And then in first row, second column slot, you would get minus 3B plus D plus 2F. All right, and then in second row, first column slot, you'd get A minus 4C plus 5E. Okay. And then in the last slot, you get B minus 4D plus 5F. And if you actually check this product, this is exactly what you get. So what would you get in the first slot? So you get minus 3 times A plus C plus 2E. Hey, that's exactly right. In the next slot, you get minus 3 times B plus D plus 2F. Hey, exactly, right? And this always works. So the fact that this expansion always works is called the column row expansion for AB. So this is a big named theorem in the textbook. So I'm going to write that theorem, and then I'm going to say what it is I actually care about. I don't care about this specifically. I only care about it because it allows me to state the spectral decomposition. So there's a theorem called column row expansion. So column row expansion of AB. What does this allow me to say? So if A is m by n, B is n by p, then we can think of the product AB as being written as a vector containing, col 1A, col 2A, so on all the way out to col n, right? There's n columns. So col n A times the vector consisting of the rows, right? The column vector consisting of the rows of B. So row 1B, row 2B, and so on all the way to row NB. So there's n of them in each case to match up here. Okay, and this is col 1A times row 1A, and so on all the way out to the last col NA row NB. Sorry, this should be a B. Right, this should be a B. There we go. Okay. All right. So this is the column row expansion. Okay, and it's nice for a variety of reasons, but the main reason it's nice for us is because it allows us to write out a symmetric matrix A in a really, really cool way, which is the following. So we apply this to a symmetric matrix A in light of the spectral theorem. Okay, and so that's what I'm going to do on the next page. Okay, so let's say that A is symmetric. Well, if A is symmetric, it's orthogonally diagonalizable. So A is P, D, P inverse, where P is invertible, but also orthogonal. D is diagonal, and I can write this as P, D, P transpose. So A is P, D, P transpose. But of course, we actually know the very nice form these things take. So this is, if I think of the columns of P, I'll call them U's. I'll call them U's because P is an orthogonal matrix, so these form an orthonormal basis of Rn. So U1 to Un are the columns of P, times diagonal matrix made up of the eigenvalues, counting with multiplicity, so there could be repetitions here. Right. Lambda 1 to lambda n, zeros everywhere else. And then P transpose, which now I can write as U1 transpose, U2 transpose, and so on. All the way down to UN transpose, right? Okay. But then I can write this, I can put these lambdas on these vectors U, and this is the same thing. So I can write this as columns lambda 1 U1, lambda 2 U2, and so on out to lambda n UN. And that's still multiplied by these rows, U1 transpose, U2 transpose, and so on, all the way down to UN transpose. Now you see what I'm getting at, right? So let's go back for a second, right? Column row expansion. Now you see where we can apply this when we think of this product written in this way, right? And we have this column row expansion. So using the column row expansion at this next step, I write this as lambda 1 U1 U1 transpose plus lambda 2 U2 U2 transpose, and so on all the way out to lambda n UN UN transpose. This is the spectral decomposition. So this is the spectral decomposition of A. You can only do this when you have a symmetric matrix in this way. Okay. Now again, where does the term spectral come from? The spectrum, so the spectrum of a matrix is the eigenvalues. So the spectrum is like it's an ancient word. It's I mean it's been out of fashion for a long time, I'm pretty sure, calling eigenvalues like this. But this, hundreds of years ago, or at least maybe even just like 150 years ago, this was spectral anything referred to eigenvalues. Okay, and so that's where the word spectral decomposition comes from. Each of these terms is actually really nice. So so here's another note. Each UJ transpose is actually what's called a projection matrix. So each of these is what's called a projection matrix. What is a projection matrix? So what that means is that i.e., for every vector x in Rn, if I were to multiply x by this matrix UJ transpose, right? If I were to define transformation of Rn given by this thing as its standard matrix, this is the orthogonal projection of x onto that eigenspace. Okay, is the orthogonal projection of x onto the subspace spanned by uj. Okay. And so, in a sense, the spectral decomposition says that a symmetric matrix is like a sum of scalar multiples of orthogonal projections onto the individual subspaces spanned by these eigenvectors. Okay, and the scaling done is the scaling done by the eigenvalues after the fact. Okay, and so this is really, really, really nice. Let's do one example of actually computing spectral decomposition, and then we'll be done for today. So here's an example. Construct a spectral decomposition of the matrix A, where you're actually given its diagonalization. So the matrix is the matrix 7, 2, 2, 4, and we're given its orthogonal diagonalization. So don't, when you're watching this, in the future, don't think that I've already computed something here. So this is 2 over root 5 minus 1 over root 5 minus 1 over root 5, or no, just 1 over root 5, and 2 over root 5 times the diagonal matrix 8, 0, 0, 3. So the eigenvalues of this thing are 8 and 3. And then on the other hand, I have the transpose of this thing. So I have 2 over root 5, 1 over root 5, minus 1 over root 5, and 2 over root 5. Okay, there we go. Okay, so if I already have this, the spectral decomposition, of course, is 8 U1, U1 transpose, where here's U1 and here's U2, right? Plus 3 U2, U2 transpose. Okay, that's easy enough. But now, what does this tell you? To actually see how this works, let's actually compute U1, U1 transpose, right? Using our row column rule. So U1 is the column vector 2 root 5, 1 root 5. And U1 transpose is the row vector 2 root 5, 1 root 5. Right? So what is that if I actually compute it? So if I actually compute this, I get 4/5, 2/5, 2/5, and 1/5. Right? And then if I compute U2 transpose, so U2 is the vector minus 1 root 5, 2 root 5. So then this multiplied by the column minus 1 root 5, or by the row minus 1 root 5, 2 root 5. So this is the 2 by 2 matrix 1/5. So minus 2/5. Minus 2/5 and 4/5, right? Okay. So then 8, if I did 8 U1 transpose plus 3 U2 transpose, what do I get? So it's 8 times this plus 3 times that. So as a 2 by 2, this would be 32/5, 16/5, 16/5, 8/5, plus 3 times this would be 3/5, minus 6/5, minus 6/5, and 12/5. If we add each entry, what do I get? 32/5 plus 3/5, that's 35/5, that's 7. 16 fifths plus minus 6 fifths, that's 10 fifths, that's 2. 16 fifths plus minus 6 fifths, that's 10 fifths, that's also 2. And 8 fifths plus 12 fifths is 20 fifths, which is 4. Hey. Right? This is A. So you can, in fact, write A in this really weird way. Now, this is extremely nice for what we're going to do next. Okay, so that's why I wanted to go over this, because it makes a lot of what we want to talk about here very easy. Even if we don't directly apply some of this stuff, having a spectral decomposition for a matrix is really nice. So anyway, so I think that's all I wanted to say for today. I think you have MATLAB due sometime soon, maybe tonight. And so what that means is that soon, sometime tonight or tomorrow, I will post your second MATLAB project, and that will be the last MATLAB project that you have to turn in, and it'll be due on the last day of class. So it'll be due, I think, December 14th, last day of class. It's a Monday, so yeah, so it'll be due that Monday, like at midnight. And yeah, that's the deal. So I'll post that sometime soon, the next couple days. Simple eigenvalue. Simple eigenvalue has multiplicity 1. That's simple eigenvalue. Thought this MATLAB was due the 30th. Oh, that's possible. Yeah, that's fine. Oh, okay. So then, what I'll do then is I will post the second MATLAB like a few days before that one is due. Then that way you have a little bit more time to work on it if you've already turned it in or whatever. You have a little bit more time to work on it. So yeah, I'll post. I'll post it sometime over Thanksgiving, then, your second MATLAB. Or I'll just post it whenever, and you can work on it whenever. Just because I posted it doesn't mean you have to start working on it immediately, so maybe I'll still post it in the next couple days, and it'll be due on the last day of class. That way you have plenty of time for it. Yes, that one's also groups. Doesn't have to be the same groups, although that would certainly be really convenient, and your TAs would probably love you if you did that. So I would highly recommend you stuck with the same groups. But the same rules apply. If you are going to switch groups, then it's the same rules going to apply. If you have issues with a group, then talk to your TA. They'll assign you a group. And that'll be that. Okay. Gustavo, there's a lot of applications of this, so I will touch on some of them. By the time we finish what we're doing in Chapter 7, you'll have seen a few. Okay, so I think that's it. So I guess we're off Wednesday, so no lecture on Wednesday, and we're way more than caught up, so I don't need those supplemental lectures that I had floated posting. There's no point in doing those because we're ahead. So we're going to have plenty of time for fun material at the end. You're just kind of doing whatever. And yeah, so no, I guess your next lecture will be next Monday. And yes, you need a group for the second MATLAB project as well. Okay, so that's it. You all have a good break, whatever you're doing, and I will see you all next Monday. Just keep an eye on the announcements. I will let you know when I'm posting something. So anyway, then I guess that's it. So I'll see you next week.